Okay, kids, let's do some vocabulary. Muy importante vocabulario, which is, we all know, Spanish and Italian combination for very important vocabulary. Now, this vocabulary goes along with the first law of thermodynamics, which we now know has an equation that goes along with it that looks like this. Remember? Yes, you do. Yes, you do. Yes, you do. So delta U, our change in internal energy, okay, that's our kinetic and potential energy, is equal to Q plus W. All right, now, there are certain situations you'll hear words like IsoVolumetric, Isothermal, IsoCoric, no, that's all the isos, and then, adiabatic. So these words, we got to know what they mean, okay? Because sometimes you'll say, hey, an adiabatic situation occurs, and you have to go, oh, I know what that means. That means no heat added. So let's go through them. Let's say that we have a situation like this, where heat's being added into a system, but there's no change in volume. All right, now you might say to yourself, Sal, like, when does that happen? You know, because we all know that when things get warm, they expand, okay? That's called, thermal expansion and stuff. We know that, we're so smart. Well, what about this? What if you drive into Walmart one afternoon in a hot 95-degree summer afternoon? You leave the windows up, you go and do your Walmart shopping. The cultural center of any universe is Walmart. Yeah, it is. And then you come back out, let's say 20 minutes later, you get into the car, you just melt. Melting, because it's so darn hot. So what just happened? Well, heat energy from the sun came into the car, and it caused the temperature to go way up. The internal energy of the car went way up, so we increased our internal energy, but we didn't change the volume of the car. You know, you go outside. Wouldn't it be more interesting if we went outside on a hot summer day and the cars all just went like, and they all expanded in the parking lot? That'd make, parking and getting in and out of your car a little more interesting, wouldn't it? Or more of a pain. But we all know that that's called a rigid container. Your car is a rigid container. A rigid container means it's not going to show any noticeable increase or decrease in volume. So the car's volume stays the same, but yet we still added heat to it. Okay, that's what I'm talking about. That's a case of IsoVolumetric. Write that down, IsoVolumetric, meaning the same volume. That's when we have a rigid container, or a container that is not going to change its volume in any noticeable effect. All right, okay, now when that happens, when we don't have a change in volume, so this is rigid container, if we don't change the volume, then there's no work being done, because we all remember from a few videos ago that work done on or by a gas is when you have change in volume. Okay, work expands, if the volume expands, or it contracts. If the volume contracts, work's being done on the gas. If it expands, the gas is doing work on the environment. Okay, so if we don't have any change, we have a rigid container, then there can't be any work being done because we get no change in volume. So remember, this equation here is P delta V. And if I don't have that because of the rigid container, then I don't have this at all. So this goes away. And that's what you're left with. Our internal energy changed in the car. It got hot in there. Okay, it's like, oh, melty, because we added heat energy to the system, changing its internal energy and cranking up the kinetic energy and cranking up the what's the stuff you call it? Temperature. Okay. That's IsoVolumetric. There's the first of our muy importante, grande vocabulary words that we need to know that's associated with the first law. All right, let's put our equation back up here. And let's try another fun word. Another fun word that goes along with this IsoVolumetric idea is one called IsoCoric. I think I said isochloric before. IsoCoric. IsoCoric is another way of saying the same pressure. So this is pressure, fancy, sciencey way of saying pressure. That means we don't change the pressure any of the gas. Now, if we don't change the pressure, well, there's no pressure in that equation. You know there's pressure in that equation. We just said that. So we know that this equation right here is the same darn thing as P delta V, or change in volume times pressure. So we know that this is when we have the IsoVolumetric, if that doesn't change. But if we don't change any pressure, if there's no pressure change, then there can't be any volume change. We're going to have any volume change, there's no pressure change. So an IsoCoric situation is another one that we're not isolating, we're not changing the pressure any. Okay, we're not changing the pressure any. We're not doing any work on or by the system. There's no pressure change, there's no contraction or expansion of the gas. So if that happens, we have the same thing happening here, that our change in internal energy equal to just the Q, just the heat being added or subtracted from the system. So IsoCoric and IsoVolumetric have the same result. Okay, we're going to change our internal energy only by heat being added or subtracted from the system, but they do it in a different way. One's volume and one's pressure. Still have the same result though. Okay, so there's two words down. We've got IsoCoric, meaning same pressure. IsoVolumetric, no change in volume. Put our equation back up on the board, plus W. Okay, what about this one? Adiabatic. Adiabatic. I think that's a body of water between Italy and Greece, the Adiabatic Sea. That's very good, Billy. Very good. Oh, wait, no, Billy, that's the Adriatic. Billy, you're so funny, Billy. Funny? No. Adiabatic means no heat. That's what that means. No heat. No heat. Did you get the Adriatic? It's funny. Yeah, that's funny. No heat being added or subtracted from the system. So there's no heat involved. If there's no heat involved, then this part goes away. And our first law of thermodynamics now looks like this. Just work being done on or by the system with no heat being involved. A situation might be like this, like maybe you work at Hannaford or some other shopping place where they have balloons. You know, they have those mylar balloons you fill with helium. And maybe you've actually filled some of these yourself. And so those things fill up pretty darn quick. You know, you get this little balloon, I want Winnie the Pooh. Okay, fill up Winnie the Pooh. Okay, Winnie the Pooh gets big really fast. So it doesn't take very long to fill that balloon with the helium. That's a situation that's adiabatic. In other words, there's no time for heat to go in and out of that system. That balloon is being blown up so quickly that the work is being done to fill that balloon. We have a change in volume. Yes, but so quick that happened that we didn't have time for heat to go in or out of the system. That would be an example of an adiabatic situation. Okay, work only, no time for the heat to go in or out, just happened too fast. So that is adiabatic first law situation, just work. All right, now we've got our third vocabulary word done. We got to get one more for a total of 4 vocabulary words that are associated with our first law of thermo. And adiabatic is no heat. We have one more, and that is, oh, we put our equation back up here. All right, there's our equation. Isothermal. Sometimes you see it as isothermic, but usually it's isothermal. All the cool kids say it that way. Isothermal situation. What does that mean? That means the same temperature, Now this thing here, right there, is where the temperature is, because this is the potential and the kinetic energy. When it comes to gases, we're talking about when gases have energy, it's all kinetic. It's just basically all kinetic. The potential energy is just like tiny, so don't pay attention to it. It's all kinetic energy when it comes to gases. So the internal energy of a gas is how much kinetic energy it has. And we all know that it's kinetic energy that will dictate what our temperature is going to be. So kinetic energy and temperature are directly related to each other. One goes up, the other goes up. One goes down, the other goes down. So the internal energy, that being where the kinetic energy is what's going to dictate our temperature of a gas. Okay? Now, if we want the situation to happen that's isothermal, that we don't change this, well, either we don't do anything to these, so that'd be kind of boring, wouldn't it? Yeah, that sounds kind of easy. I'll take it that way. No, Billy, no. No, when we're going to deal with this and not allow this to change, if one of these goes up, then the other has to go down an equal amount. There has to be equal changes in both of them occurring to keep things fair and balanced. Balance in the force, Luke. Yes, in order to have balance in the force and maintain the same temperature, If there's work being done, there has to be a heat combination of those two things being equal to each other. All right, let me give you an example. Let's say that we take a balloon. You all like balloons. Who doesn't like a balloon? Come on, what person does not like a balloon? Do you know anybody who doesn't like a balloon? Exactly. So I'm talking about everybody likes balloons. So you got a balloon, and you just, you went to like Hannaford. You got yourself a nice Winnie the Pooh helium balloon, and you're all happy with it. You're walking outside, and it's January. Okay, what happens to the balloon when you walk outside? Right? Okay. Or what if you walk outside and it's July, 90-degree July day. You walk outside in the sunshine, and the balloon's going to actually expand. Okay, when that happens, okay, I'll draw a balloon. Balloon. It's a nice balloon. Scale of 1 to 10. I give that 9.7. Good balloon. If you walk outside and the sun, Mr. Golden Sun shining down on me, then heat. Wiggly lines with is universal for heat energy. We all know that, okay? Everybody knows that. You do that in Germany, they go, you mean heat, and you will like it. Okay, that's German physics guy. Now, so heat, put some cues here. Heat's coming in, I'll say from the radiant, happy sun, into your balloon. All right, well, what does that do to your balloon? You know, it expands the balloon. So the balloon is going to change in volume. We'll draw the expanded balloon in dots here. So the balloon pushes on the environment. The balloon does work on the environment. So in order for the balloon to expand, it's got to move air out of its way. Get out of my way, air, get out of my way. So it's doing work on the environment, pushing the air out of the way. So work is being done by the balloon, Do you remember when work is done by something? What sign do we give that? Is that positive or negative? Work being done by? That's negative. Very good, Billy. It's a negative, so that's negative work. So that means that work is being done by the balloon, so it's losing energy by doing that work. So that would be negative work. But at the same time, we're gaining heat energy. That's positive heat. In fact, that's how you designate whether or not heat's being lost or gained, positive or negative. If heat's being gained, it's positive heat. If heat's being lost, negative heat. So Mr. Golden Sun comes down, gains heat energy into the balloon. That causes the balloon to expand. So work is done by the balloon on the environment. The environment gains work, energy, and the balloon loses it because it's doing work to push the air out of the way. If that happens at a relatively slow pace, then we could have a situation where we have just as much heat going in as expansion and work is going out of the balloon. We have fair and balance. We have these two things equal to each other, and therefore the temperature of the balloon won't change. So remember, it's all about isothermal, the temperature not changing. All right, so temperature doesn't change, that's equal to that. We have what's called isothermal, and if that happens, check it out, that means there's zero change here, which means those two things have got to be equal to each other. They have to be equal to each other. One goes up and the other goes down the same amount. So that means heat lost or heat gained is equal to W lost or W gained. So this is our isothermal situation after taking a peek at it and looking at our first law. That's what the first law breaks down to in isothermal. Now, those are our 4 words, okay? IsoCoric, IsoVolumetric, a quick review. Those, the W goes away, no pressure change, no volume change, we're not gonna get any work done. So that means, nope, that's not a 0 anymore. That's our delta U. That's equal to that, okay? Then we have the adiabatic. Adiabatic means no heat. Take the heat out. All your work's gonna do all the delta U, all the internal energy change. And then last but not least, we have the situation where it's isothermal, meaning that the heat gained or lost is equal to the work done or lost on the system, not changing the temperature. If you're not going to change the temperature, you want that to change. Those have got to be equal to each other in order. And you got to have both of them too. You can't have just one of them and get a 0 temperature change here. You got to have both of them happening at the same time in equal amounts. All right, okay, that makes like a gift and wraps up our vocabulary for the first law. And doggone it, you better know that vocabulary. Trust me, you better know it. All right, talk to you very soon, very soon.